Hey everybody, on this example, we're going to be looking at the example 318 on page 191 and 192. And for this one, we're going to be using our two rules that we've been working on for probability, the multiplication rule and the addition rule. Here we go, a little bit of a longer one. Studies show that about one woman in seven, 14.3%, lived to be 90, developed breast cancer. Suppose that those women who developed breast cancer, they have a false negative test 2% of the time. Also suppose general population of women, the test for breast cancer is negative 85% of the time. So we'll let B be a woman developing breast cancer and N be a negative test. Suppose one woman is selected at random, and then we'll answer all these questions. What's the probability a woman develops breast cancer? Well, that's given to us right here, 14.3%. We can move that decimal 2 spots to the left, 0.143. What's the probability that a woman tests negative? That's also given to us. 85% is 0.85. Given that the woman has breast cancer, what's the probability that the test is negative? That's also given to us here, 2%, which would be 0.02. And to write this out, we would say the probability that a woman tests negative given she has breast cancer. So that's where the given is going to show up. What's the probability that the woman has breast cancer and tests negative? So this one is a little bit different because it's the probability a woman has the breast cancer and she does need to test negative. So on this one, we were looking at the subset of people that have breast cancer, but this is the probability that a woman has breast cancer and then they need to test negative. So it's the probability of cancer and a negative test. So to do that, we go back to our formulas. Right here, we can look and see the probability of A and B is the probability of A multiplied by the probability of B given A occurred. So we're going to use that down here. The probability of B, so the probability of cancer. Then we're going to multiply that by the probability of a negative test given we have cancer. So the probability of cancer is small, about 14%. And then the probability of a negative test given we have cancer is very small, just 2%. And so we have a very small chance that a person has cancer and will have a false negative test, which makes sense. Like this cancer is hardish to get, and the false negative result is also very hard to get. Okay, the next part is looking at or. What's the probability that the woman has breast cancer or tests negative? This is going to be a very wide swath of people now because it's going to be all the cancer people, but also all the negative tests. So we're going to calculate this. We take the cancer people, the negative tests, and we're going to subtract the intersection of those two. Because if we think about these overlapping Venn diagrams, if we go back to we worked on here, so if we take A and B, and if we add those together, we're going to count this middle part twice. So what we want to do is subtract that middle part once, and we just count it just a singular time. So we take and we subtract that middle part just once. So here's cancer, here's a negative test. Remember, that was just a negative test in general. Then we subtract that intersection of those two. So 99%, 0.99, about 99% of the time, we either have cancer or a negative test, which kind of makes sense. Either, you have cancer or you test negative for it. Having breast cancer and testing negative, independent events. So we want to think, does having cancer impact the probability that a negative test will occur? Well, most likely, if this is a good test, we want these to be dependent on each other because we want the test to find the cancer. So we want these to not be independent. We want the test to be dependent on whether or not cancer is there. So to prove this, we compare these two probabilities, the probability for a negative, 85%, and the probability for a negative test given we have cancer, 2%. So if we have cancer, our chances for a negative test go down a lot, which makes sense because it's finding the cancer and letting us know. So since these probabilities don't equal each other, they're not independent. Are having breast cancer and testing negative mutually exclusive? So that's asking, can breast cancer and a negative test, is there an overlap for those? And the answer is, well, are they mutually exclusive? The answer is no. And it's because they're not separate. They have a little bit of an overlap. Cancer and a negative test, yes, there is 0.0029 of the people. So about 0.29% of the people out there that have cancer then get that false negative test. In order for these to be mutually exclusive, the intersection of these must be 0. All right, that's it for this one. Thanks.